Statistical power is an issue that most data analysts and researchers will face, and many don't really think about it until it's too late, until the study has already been conducted. But it's usually wise to think about statistical power considerations prior to conducting a study. For our purposes for this class, we just want to define it and be aware of its existence. But for someone who goes on to conduct research studies, they would want to study statistical power in depth to make sure that they're conducting studies that have the chance of detecting whatever it is they think exists in their data. So let's define statistical power as a probability that a statistical test will detect an existing effect. So probabilities range from 0 to 1. 0 means it has no chance at all. It won't detect anything. It can't detect anything. 1 means it's absolutely guaranteed to detect something. In reality, statistical power will not be 0 or 1. In almost all cases, it'll be somewhere in between. Hopefully higher rather than lower. So basically, it's the probability that if we're talking about differences between means, it's the probability that the test will detect a difference between the means and the population, assuming a difference exists. So statistical power is only defined in situations where we assume an effect exists. If the null is actually true, statistical power is not actually defined. Most researchers, although this varies widely by subfield and field and what study design, but most researchers should aim for at least 0.8 power. So that gives you an 80% chance, so to speak, of detecting an effect that's actually there. Another way to define power is 1 minus the probability of a type 2 error, which you might recall we defined as beta. So 1 minus the probability of a type 2 error. A type 2 error is missing an effect that's there. So if we take 1 minus the probability of missing an effect that's there, we get the probability of detecting an effect that exists. So statistical power is very important for researchers. They generally want to design studies so that they have a sufficient amount of statistical power to be able to detect something if it is there, to be able to reject the null if the null hypothesis should be rejected. So what influences statistical power? There's a number of things that influence statistical power. We're just going to talk about some of the most important. One is the effect size in the population. So a larger effect size. So an effect size is basically a measure of the strength or magnitude of an effect. So we're talking about differences between means. The further the means are apart, generally speaking, the stronger the effect. If we're talking about relationships between variables, the more strongly related the variables are, the stronger the effect size will be. So if it's a larger effect, it kind of makes sense that it'll be easier to detect and you will have more statistical power. Whereas if it's a weaker effect, like let's say it's just a small difference between means, it might be small, but it might also be important. But if the effect size is small in the population, it'll be harder to detect and we'll have less statistical power, all other things being held equal. Sample size. Sample size is incredibly important to statistical power. So small sample studies tend to have less statistical power. So if one runs a study and has only a small number of participants and the effect size that they're trying to detect isn't enormous, they're going to have a hard time detecting anything. So sample size is important. More people, more statistical power, or more cases in the analysis, the more power one will have to detect an effect, assuming it exists. Another thing that is related to statistical power is your significance criterion. So if alpha, your significance criterion, as you remember, is the maximum probability that you're willing to accept a type 1 error, if that alpha is very low, that's from the standpoint of type 1 error, that's good because you're protecting against type 1 error, but from the standpoint of type 2 error, And power, it's not so good because it makes it harder to detect things that might actually be there. So there's kind of a trade-off between lowering alpha. The more you lower alpha, the more likely you're going to be lowering your statistical power, although you're protecting against type 1 error. So to put simply, higher alpha leads to what's called the less conservative test. It means it's easier to reject a null, which gives you more power, but it will also make it more likely that you could be making a type 1 error. And a lower alpha is a more conservative test, which will protect against type 1 error, but will give you, all other things being equal, less statistical power. It's also important to take into account the reliability of the measure. So a more reliable measure will, on average, give you more statistical power because there's less error in the variable that you're measuring. A less reliable measure will by definition have more error, which will make it harder to detect an effect and will lead to less statistical power. So it's important when choosing variables and measures to test hypotheses to try to choose ones that are reliable and relatively low in terms of error. There are other things that affect statistical power. For instance, whether it's a one-tailed or a two-tailed test. So a one-tailed test will give you more power in the direction that you predicted, but it won't give you any power in the opposite direction. Whereas a two-tailed test will give you slightly less power in the direction that you expect your results to occur in terms of the research hypothesis, but it'll also give you some power in the opposite direction in case you are completely wrong. So here's a visual depiction of statistical power. So you can imagine that this is the distribution of means under the null hypothesis, and this is the distribution of means under the alternative hypothesis. And you can imagine, so here we've set it up where there is a difference, because you see the mean for the null is different from the mean for the alternative. So there is an effect here in reality. And what you can see is here in blue we have what we're going to call the rejection region, or you could call the region of significance, and that will be where we would be able to reject the null hypothesis and provide evidence for the alternative hypothesis. Here the alternative would be, it looks like that the mean obviously for the alternative is higher, for this population rather, is higher than the null hypothesis distribution. So that part of the alternative hypothesis distribution of means that is to the right of the significance criterion, or our rejection region, we can think of as statistical power. Whereas to the left, since the alternative hypothesis is true here, to the left we can think of it as a type 2 error. So it's kind of an illustration of why power can be defined as 1 minus the probability of a type 1 error. So here we have a website that's a pretty nifty interactive visualization of statistical power, and I'll provide a link for this and the resources page on Blackboard. So I'm going to ask it to calculate for power, and we're going to leave alpha right now at 0.05. We're going to have a sample size of 20 and effect size. We haven't covered effect size yet in specific terms, but this effect size, Cohen's d, is basically a measure of the difference between means divided by the standard deviation. So it's in standard deviation units, and we'll leave it as a two-tailed test for now. So you can see here we have a difference between the means. There's a fairly large effect. We have a somewhat small sample, and we have a two-tailed alpha of 0.05, and that gives us a power of 0.8, which is like the power that many people aim for, like at minimum. So you can see what happens if you up the sample size. So let's up the sample size to like 70 something, and you see we get a lot of power. It says 100. It's not really 100, but it's rounding it to 100. Let's make it a bit lower. And you see if with larger sample size we get more statistical power, greater ability to reject the null hypothesis, as it should be rejected here because it's set up so that there is a difference. So let's bring this back down to 20, or there we go, 20, and let's see what happens if we have a smaller effect. So if we had a smaller effect size, let's say around 0.2, we see that now it's much harder to detect an effect. So 15.15 or 15% power would not be sufficient. We would not want to run that study. So in order to have more statistical power in this situation where it's a very small effect, or a rather small effect that we're trying to detect, we would need to have a larger sample size. So with a sample size of 134, we have 0.64 or 64% power. Still probably not going to cut it. Let's see if we can get it up to about 0.8 with a sample size of around 200. We can get up to a sufficient amount of power. So as you can see, with a small effect size, we would need a much larger sample to have a good probability of detecting an effect. Now also, we don't really have a lot of wiggle room with the significance criterion. The alpha, usually 0.05, is about as high as is acceptable for a type 1 error rate, a priori type 1 error rate. But if we increase that, let's say to 0.1, you'll see we would get a bit more power. And if we decrease it, then we get less power, right? So we usually don't have a lot of freedom to move this around above 0.05 to give ourselves more power. We can lower it to protect against type 1 error, but remember that that will lead to having less statistical power. So usually the solution is, if power is an issue, is to try to up your sample size. Also, whether it's a one-tailed or a two-tailed test has some impact on power in the direction that the researcher might have predicted. So a two-tailed test here with an effect size of 0.2, a small effect size, a sample size of 20, a small sample, and a alpha of 0.05 really doesn't give you a lot of statistical power. If we switch to a one-tailed test, we'll get a bit more. You see it went up a little bit, but it's still not a lot. What we would need to do here is, if we were running this study, we'd want to make sure we had a sufficient sample size to have a good amount of power to detect an effect if it's there. Sometimes if you do sample size calculations before a study, you might determine that the sample size you need to detect a small effect is so large that it might not be worth your time and resources to actually run the study. And it's good to know that before running the study, then find that out after the study has been run. Unfortunately, it has been the case for decades in many areas of science where researchers just neglect to do sample size calculations, and they just run the study using a rule of thumb or just a number they picked out of thin air in terms of participants, and they may not even realize that they ran a severely underpowered research study. So I encourage you to play around with this visual interactive tool to understand how alpha, sample size, effect size, and whether it's a one-tailed or a two-tailed test influences statistical power. And remember, power is the probability of rejecting a null or detecting an effect, assuming that an effect is there in the population. So to conclude, I just want to talk a bit about the importance of replication. So any given study is going to yield a p-value. And a low p-value can occur by chance. The p-value is basically the probability that your results are due to chance, or the probability that you would reject the null hypothesis even though the null hypothesis is true. So it can occur when there is practically no effect at all. Like, you can get a low p-value when there's no effect in the population, especially if you have a small sample. And you can also get a non-significant p-value by chance when there is actually an effect, especially in small samples. So small samples can be very volatile in terms of what can be detected and what is trustworthy in terms of what is detected. So the results of one study, especially the results of one small sample study or experiment, are rarely conclusive. So replication is incredibly important in statistics and in science. So if many similar experiments or studies demonstrate or fail to demonstrate on average an effect or relationship, then that would build up more evidence either for or against the effect or relationship. So replication is critically important. So it's incredibly rare for one study to be the end all and be all, to be conclusive about a given effect or relationship. So basically, scientific results should be replicable to be of general value. The result of one study could be important, but the result of one study could be a type 1 error, or the result of one study could be a type 2 error. But if there have been dozens of studies or even hundreds of studies on a topic, and we can aggregate the results, and there's a statistical technique called meta-analysis, which allows us to analyze the results of many studies on the same effect, and then we can get hopefully a clear and convincing case for the presence or absence of an effect, and also an idea of what is the approximate strength of the effect in the population, assuming that the meta-analysis is conducted effectively. I thank you for listening, and I hope you enjoyed that as much as I did.